So this lecture is about dimension reduction. It will be a little bit different from the lectures that have been so far. So there will be a little bit less hashing at the moment. Well, connection to hashing will start appearing towards the end of this lecture, and especially in the lecture tomorrow. But from the other perspective, this is really about a lot of geometry. So this is kind of entering the realm of geometry. It will be mostly high-dimensional geometry, and it has been at least partially motivated by some of Graham's examples where we compute frequencies and eventually have items, and you can think about the frequency vector as being a high-dimensional vector, right? You have n dimensions, and some of the tools for doing some hashing or some sketching have been influenced by what has happened in high-dimensional geometry or the tools from there. In particular, Johnson-Liljestrauss lemma, but that Graham mentioned, and at least most of the lecture will be actually about Johnson-Liljestrauss lemma. Before that, I want to motivate a problem that I want to give one particular problem that is one of the fundamental problems in high-dimensional geometry, high-dimensional computational geometry, and it will be the problem that we'll be solving both today and tomorrow. Okay? And this problem is nearest neighbor search. So, I mean, phrasing this problem in different ways has motivated a lot of tools and techniques in high-dimensional geometry and perhaps in hashing as well. All right, so let me define the problem. So it's a data structure question where we have a set D of points. We want to pre-process them somehow, so that later at query stage we're given a point query Q, and we need to report the point that is closest with the smallest distance to the point query Q, in this case this point P. Okay, so motivation so first of all, this is high-dimensional situation. So the dimension where the points come from can be really high dimension, and where does this come from? So this comes from kind of general area of similarity search, where we think about the points as being some objects. For example, they can be some depictions of images, and the distance can model dissimilarity measures. So these are, for example, we can think about the points as representing some kind of images. For example, these are images from a very classical data set called the list of handwritten images. And you can imagine that we have a bunch of images that are already labeled, whether this is a 2 or a 7, and you are given a new image and you want to label whether this is perhaps a 2, and you do this by finding the most similar image and essentially using that label as a predictor. How does this look? Why is this high-dimensional problem? Well, you can, one way to measure this is take this picture and essentially, maybe you sample it down. So I think these pictures are 28 by 28 pixels, and you can write them as a binary matrix essentially, right, with 28 squared dimensions, where each dimension is 0 or 1, or the corresponding pixel is 0 or 1. And you can compare the images, measure kind of the distance or dissimilarity between them is by computing Hamming distance between these two vectors, right? And these vectors are naturally high-dimensional, 700 dimensions or so. Naturally, this, I already mentioned that this is essentially, in machine learning, this is called the KNN rule, the nearest neighbor rule. This is one of the classical classifiers. And as such, it has been used and is being used in many areas, such as speech, image, video recognition, or bioinformatics, quantization, and so forth, right? I mean, this looks a little bit of a naive way to measure the distance between images, and indeed, you can imagine different distances between such objects, for example, Hamming and Euclidean, or eddy distance, which would measure perhaps dissimilarity between text where you can do typos, or even more complicated measures like F-mover distance. And indeed for images this is perhaps a little bit too naive, but anything that is even more complicated will have this problem underlying it, at least as hard problem, right? So many of these other things will reduce to this kind of situation. And also, another perspective is that nearest neighbor search can actually be used as a primitive for many other problems in geometric settings. For example, if we have a data set and we want to find the similar pairs, or the closest pair problem, or if we want to do different kind of clusterings, so many of these problems will need nearest neighbor search in one form or the other. So it seems to be a fundamental problem here, and there's a lot of research on kind of trying to solve this problem. And you know, let's start with something kind of very simple being say two-dimensional case. What happens in two-dimensional case? Before we go into high-dimensional situation, so the classical data structure is to compute a Voronoi diagram, and given a query point Q, you want to do what is called point location. Basically, given a point query Q, point location means finding this zone. I'm sure that you guys have seen this Voronoi diagram before. And basically, what this data structure kind of achieves at the end is, assuming good point location data structure, it will get kind of performance space which is linear in n is the number of points size of a data set, and query time is order log n. I'm sure people tell me that this can be done more efficiently, but let's do it this way, right? Even achieving these will be really, really good in general. So in high-dimensional case, we won't be able to achieve this, right? But even setting this up as kind of golden goal would be really good. So in high-dimensional case, unfortunately, we can. There are essentially two extremes of what we can do. Things become much harder, and all the exact algorithms degrade very rapidly with dimension d. There are essentially two things that you can do, kind of two extremes. One is to do this similar thing, kind of, a Voronoi diagram for dimension d. You can do it, and it will have kind of nice query time, something like log n times dimension. You can often think about dimension as being, let's say, logarithmic. Let's say the space unfortunately will be something like exponential in dimension, right? Which is just not practical, not doable. The other option is to not do anything, essentially, to be lazy and not to do any preprocessing, and then you will have a very nice space. Unfortunately, the query time will be something like n times d. Okay, so this is the situation, and this motivated studying approximation algorithms. And tomorrow we'll see some more algorithms for this. But this is kind of a problem. This is a problem to keep in mind. And so I just wanted kind of to introduce this problem, and this will be one case where, say, dimensional reduction will help a little bit. Okay, so this was a problem. This was kind of an aside, kind of a motivating kind of example to keep up there. So going back to dimensional reduction, here is kind of a natural thing to do. So if high dimension is really a problem, and this is the slide that should really tell you that high dimension is really a problem. But all this has a name. It's called curse of dimensionality. Kind of the higher dimension, the worse it is. So one approach is like, okay, so if dimension is high, can we reduce it perhaps? Is there a way to is high dimension really necessary? And this is one motivation kind of for dimension reduction. So if it is high, let's try to reduce it, and we'll think of original dimension as being d, and the smaller dimension, the target dimension, as being k. These are the numbers that will be. These are the letters we'll be using for the rest of the talk and lecture. And I guess pictorially, here we have a bunch of points in three-dimensional space. Maybe we can reduce them to one dimension while preserving all the distances, right? So if we can do this, we kind of get rid of this curse of dimensionality, right? And in general, this is not possible. I mean, if some of the classical things in geometry will tell you, like, well, if you have these points and they really have this two-dimensional or three-dimensional structure, you cannot just flatten them out. Some distances will be distorted. Some distances will go to zero, for example, right? There is nothing that one can do. But it turns out that one can do, if one can do dimension reduction if one thinks not about the entire, say, three-dimensional space or high-dimensional space, but thinks about particular set of points. So if we had a particular set of, say, n points in high-dimensional space, we can try to do dimension reduction. And this is the classical Johnson-Strauss lemma from 1984. And most of the lecture will be about it. And let us see what kind of what does it mean, for example, for our nearest neighbor search application. So as I mentioned, one of the kind of the only really practical algorithm that is for nearest neighbor search exactly is not to do anything and then to do trivial scan, right? And trivial scan of all the points will take time, which is n times the dimension. Right? This is the query time, because for each point in the data set, we will compute the distance. Computing the distance, the under Euclidean distance, it takes time d, right? Order dimension. And if we have such a dimension reduction into much smaller dimension k, we can at least do this. We can reduce the query time to something like order of n times k plus time to reduce to do the dimension reduction for our query point. Right? So, I mean, assuming this is relatively small. I mean, this in particular this should not depend on n, right? It should not have a strong dependence on n. We have reduced essentially the query time from n times k to n times k. Right? This seems like like a small reduction kind of. I mean, I have to tell you like what is k and stuff, and we'll go there. The idea is that k will generally be much smaller than dimension d, and this seems like like we've made a small step. And the truth is that in practice, a lot of the nearest neighbor search is solved this way. Essentially, people do dimension reduction, and then essentially you do a linear scan. And there are many reasons for it, some related to caching, some relating to being able to reduce dimension to very small k and do these distance computations very, very fast. But this is something that does happen in practice. Perhaps dimension reductions are a little bit more specific, but I mean, they're essentially motivated by Johnson-Strauss lemma. Okay, so this is the application. This is kind of what we want to achieve. So now let's talk about the actual dimension reduction. Right? I'm curious how fast I should be going. How many of you have seen Johnson-Strauss or the proof of it? Okay. Okay, good. So I guess about 40%. Normal speed. All right. So this is the statement. So just to be clear, what exactly we're proving. What we are proving is the following. So first of all, it is basically there will be a map. So notation L2 denotes Euclidean space. So L2 to D essentially denotes Euclidean space of dimension D. This is Euclidean space of dimension K. So we're saying that there is a linear map, randomized linear map, let's say function essentially, F, that maps high-dimensional space, high-dimensional Euclidean space dimension D to dimension K, that preserves the distances between any two vectors, between any given vectors x and y, up to factor 1 plus epsilon, and this is what it means exactly to preserve distance up to factor 1 plus epsilon, right? And this is with some probability. And this is essentially what is the probability. So the probability, this is the probability of failure. And the probability of failure that should really kind of how you should think about it is that it's really decays exponentially of the target dimension k. There is some dependence on epsilon on the target dimension, and you can think about epsilon as being a constant. But the idea is that the probability decays exponentially in the target dimension k. Yes.
Is probability for the product structure?
No. So for
each pair.
So you construct a function f, right, which is just it's a function f that doesn't see anything essentially. It's oblivious. What it's called, such that for any given x and y, this holds with this probability. This inequality holds with this probability, right? For any x and y.
But when you say that it's a randomized, doesn't that also mean there is a randomized, or will you just have randomized?
Right.
Can you repeat the question?
Sorry?
Can you repeat the question?
Yeah, so the question is, if it is a randomized linear map, doesn't this imply, by probabilistic method, right, that there exists a function f? So, in some for a particular two vectors x and y, yes, this is indeed the case. For particular x and y, there exists a function f that will achieve this. But what we're saying is that there exists a randomized linear f that works for all x and y with some probability at the same time. It does not imply, this does not imply that it will work, that there exists an f that will work for all x and y at the same time. Basically, depending on how f is chosen, it will work for some pairs, but not for all other pairs. Okay. I mean, we know that it cannot work for all pairs x and y just by pecking bound. We cannot flatten a high-dimensional space into a smaller dimensional space. But it will work for parts of the space, kind of. That's the idea. And how can we use this, right? So, for example, for nearest neighbor application, we need to really preserve the distances between n pairs, right? These pairs being the query point and every of the data set points, right? And there are n pairs, and this is, sorry?
N squared.
We don't care about distances between points in the data structure, data set itself. If I want to compute a nearest neighbor, what the distances that I need is distance between the query, point number 1 in data set, point number 2 in data set, point number 3 in data set, and so forth. There are n pairs only between the query and everything in the data set. It's not n squared because you don't care about distances of points inside the data set. Right? Anyway, so you have to, it should be n pairs. So if you want to preserve distances about n pairs, you want this probability to be something like 1 over n. And if you plug in the numbers, then essentially the target dimension that you need, what you need to set k to be is log n divided by epsilon squared. Okay, so if we say use this k, then this scalar probability becomes inversely polynomial in n. Right? And remember when time to compute, we'll care about what is the time to compute this map, and time to compute this map will be actually k times d. I mean, you don't see yet why, we'll see later why. It's k times d. Okay? All right. So this is the statement. I mean, if there are questions about the statement, now is a good time to ask. All right. So basically, now we'll show how to construct it and why it works. Really the idea is to project the data set, project the space, this map, is really a projection into a random k-dimensional subspace. Right, so we start with a really big d-dimensional space, we take a random subspace of dimension k, and we project the points there. Okay, this is it. Now let me, let's go slower a little bit. So, the statement even makes sense for k equals 1, so let's try to construct some kind of embedding into one-dimensional space. Right, so for one-dimensional space, we will say, basically the statement says that there will be some constant approximation with constant probability. Right, so let's do at least that. And what do we do for k equals 1? Here is the embedding. Here is this map. Right? The map is very simple. It is just a sum of, so mapping a point x is just the sum of ji's times xi are just the coordinates, right? And ji's are normal Gaussian distribution. Okay, so you choose ji's from this normal distribution, and this is your map. And this is the picture of the Gaussian distribution. This is the probability distribution function. Some first two moments. It's centrally distributed and has variance 1. Essentially, this is what it says. So why Gaussian? I mean, I want to avoid as much as possible formulas. I mean, obviously, some things in high-dimensional geometry kind of will involve formulas, but I really want to kind of give the intuition, and this is the intuition. So why Gaussian? Really, why we use Gaussian is because of what is called stability property, namely that for any x size, if we take this kind of sum of Js times xi, it is a random variable, right? It depends on J's, right? And it is distributed as norm L2 norm of x, basically Euclidean length of x times g, where g is another random variable, and it is distributed as a Gaussian. Right? This is the property that we use, right? And if you haven't seen this property before, then this is what you should remember from this lecture to start with, right? Another way to say this, the same thing, it's essentially equivalent, is to say that if we take this vector, take a d-dimensional vector whose coordinates are g1, g2 up to gd, right? It's a random vector, then it is centrally distributed, meaning that if we take this, I think there is a picture, if we take a vector which is distributed according to this distribution, then it has a random direction in the dimensional space. Okay? So basically, these two vectors that should be of the same length have the same probability of appearing. Okay? And so then this sum can be seen as a projection of a vector x on this vector g, right? And since it's symmetric, then this sum can only depend on the length of x, right? Because there is no direction that is preferred. So then we can only depend on the length of x, and essentially this should be some kind of length of x times some random variable, and it happens to be also Gaussian. Okay? And to see why this is centrally distributed, I don't have any kind of better intuition than essentially writing two-line proof. If you plug in PDF kind of, and you look, how does a two-dimensional Gaussian look like, and essentially PDF will depend just on the length. Basically, A and B are the coordinates, it will depend only on the length, on the distance from the center, right? So basically, using the stability, essentially this means that this sum, which is essentially our function, depends on the two norm of x, right, times some Gaussian variable. So it goes in the right direction, right? I mean, at least it doesn't depend on the structure of x; it depends only on the length of x. Right? So let me complete the proof for this one-dimensional embedding. So again, our map is this sum of Gaussians times xi, and for any x, this f of x is distributed as 2 Euclidean norm of x times some Gaussian variable. Okay. So one additional property that I think Graham mentioned that is very useful in sketching is that this map is linear, meaning that it satisfies this equality, and it simplifies a lot of some of the proofs. To prove the dimension reduction in one dimension, we want to prove that after we've reduced the dimension, essentially, if we compute the Euclidean distance in one dimension, then essentially we say that this distance between f of x and f of y should be roughly equal to the original Euclidean distance between x and y, at least with good probability. And this is what it says. Because of linearity, it is okay to essentially talk about norms as opposed to distances, meaning just to say that if you define z to be equals x minus y, then this is equivalent to saying that f of x, the absolute value of f of x is roughly equal to the Euclidean norm of z. So this is absolute value of f of z is approximately equal to the Euclidean length of z. And the proof is equivalent to prove that the squares of these are roughly equal. And now, essentially here is a claim, and it really follows very simply that for any x and y, if z is equal to x minus y, then first of all, the expectation of this is right. And standard deviation will be small, proportional to the expectation. Right. So this essentially will prove that that this holds up to constant approximation with constant probability. And I mean the proofs are really simple and just follow from kind of Gaussian distribution properties. For example, the expectation, you're computing what is the expectation? Expectation of f of z squared. If you plug in what is f of z, it is exactly Euclidean norm of z times Gaussian squared, like using this property. And this is exactly equal to length of z squared. Right, and I won't compute the standard deviation, but it is exactly the same type of calculation. Okay, so, I mean, again, the stability properties will say that. And now just going for full dimensional reduction, I mean, it doesn't look much different from one-dimensional reduction. What we do is we have k coordinates that look exactly the same. Okay? So basically f of x, so our entire map, will be just a lot of products between x and these Gaussian, high-dimensional Gaussian vectors. Right? So now G1 is a d-dimensional vector whose each coordinate is distributed as a Gaussian variable. And you have k of these, I mean basically the target dimension. You have this divided by root k, which is just a normalization constant, just to make sure that we get the right scaling. And another way, a much more convenient way to look at this is to say that this is essentially equal to x multiplied by a matrix G with the scaling factor in front, where G, just pictorially, will look something like this. So this is dimension D, this is K, and this is our vector X. Right, so this will be our f of X. Okay, so the actual map where this map G is really, each entry is identically distributed as a Gaussian variable. Okay? And again, now what we want to prove from this is that again, norm of f of z is an approximation, 1 plus of approximation to the original vector of vector z. Again, for z being x minus y. We're looking at the distance between 2 points, x and y. And we want that the probability that this happens is exponentially, but the failure probability is exponentially high in k. Does this make sense?
Yeah.
Okay, good. Yes, like when it's quiet, I'm not sure whether it is too slow or too quick. Okay, good. All right. So again, I mean, I won't fully prove this, but I mean, I'll show you essentially why this is true. Okay, but if we repeat this one-dimensional embedding k times, then essentially we will get concentration such that the failure probability is exponentially small in k. Concentration. So again, using the stability property, each of these coordinates is distributed as the length of z times some Gaussian random variable. Right. So using the stability property on each particular coordinate, essentially for each row of that matrix G, we get this, right? And then you compute what is the norm of f of z. So the norm of f of z, you can pluck out this norm of z squared separately because it's a common term to everything. And then you have basically this term, which is 1 over k. This comes from the normalization, 1 over root k. sum over dimension I of AI squared, where AI again is distributed as Gaussian. Right? So this is what we get as a norm. And what we want to prove is that this is concentrates around norm of Z squared, which essentially requires us to prove that this random variable concentrates around 1 with very good probability. And so this distribution, this results in some kind of random variable. Note that it doesn't have any parameters except for k. And so it actually has a name. Again, if you want to impress your friends with some fancy names, it's called chi-square distribution of k degrees of freedom. This is where I'll just pull a fact. But this distribution actually concentrates very well. The idea being the following. It's not like one can compute it, right, and prove. But the idea is that it is not surprising that this happens. Namely, this is a sum of essentially squares of Gaussians. So Gaussians concentrate well, right? And we have sum of k things, right? And sum of k things usually concentrate as exponentially well in k. And it is essentially akin to central limit fish. Note that it is the good part, why this holds is that this part does not depend on any of our x's or z's. Right? It really depends just on k. So it is a random variable that depends just on k. Okay. So this is what I wanted to say about the proof of Johnson-Strauss. It requires this fact that I didn't prove, but if you really want, we can prove it. Just to wrap up, what I want to say about Johnson-Strauss is that this is essentially this is the map, which is just the best way to see it is essentially up to normalization factor. It is just a matrix G times X, where matrix G is this k by d matrix, where each entry is distributed as a Gaussian variable. And then Johnson-Strauss lemma says that basically the norm of f of x is a 1 plus f approximation of the original norm of x. So going a bit further, one thing that has been proven, in particular by Akleopas, this paper, is that you can use 1 plus minus 1s instead of Gaussians. So with matrix G, it is okay if it is actually each entry is a random plus minus 1 as opposed to a Gaussian variable, which is a little bit nicer because you just sum up numbers as opposed to multiply by these Gaussian distributed variables. And as you mentioned, this is actually related to Alon Mathieu-Zegedi paper, which showed how to estimate L2 norm in streaming fashion. The difference being that Johnson-Strauss, I guess, it has appeared about a decade earlier. Two is that it actually proves a high probability bound. Okay. There are disadvantages also about, it takes more time to compute, and it uses more randomness. Right. So, so it has disadvantages as well. Okay. So actually, this is what I want to say about, the original Johnson-Strauss. The next thing is really I wanted to discuss what is about the time to compute with Johnson-Strauss lemma. Are there questions about the lemma itself? because the next thing we'll try to do is actually to speed it up. So, okay, all right. So this is, again, this is how the embedding looks like, right? And now, what is the time to compute this function of x for a given x? It is essentially a product of a matrix with x, and the time it takes is k times d, because our matrix is of size k times d. And it is a dense matrix, so we have to compute it. And at the same time, it is a natural question to say, can we do it faster? I mean, we have an input of size d, the output is of size k. Maybe we can do in essentially order d plus k time. It should be order d time, since k should be smaller than d. Yes?
In the end, you want to have an addition of two things, right? One is the time it takes to do this reduction, and then the other thing is something of the order k times d, right?
Sorry?
And then afterwards you would do this trivial scan. What is the thing you're adding? Sorry,
you mean?
Oh, it's
you mean that?
n times k, of course.
Yeah, n times k.
Okay, thanks. Sorry.
So yeah, I mean also there is it is independent kind of question, but so dimension reduction is used in many other places. So nearest neighbor search is probably one of the very simple applications. It is actually used in many other places as well, and it would be very nice to try to make it faster actually. But yes, I mean this is nearest neighbor search is one of the applications. It's also, I gave one way to use dimension reduction for nearest neighbor search, which was particularly simple to state, but there are other ways to use it also for nearest neighbor search and for other applications, and there this difference would make a difference actually. I mean, making Strauss faster will make a difference.
Okay.
But so Strauss is probably one of the pillars of high-dimensional geometry. And it relates to things like concentration of measure, and it should relate to other things in high-dimensional geometry making faster, essentially. And yeah, I mean, it is a question itself. Okay. All right. So, and the answer, why I'm talking about this, yes, I mean, we can make it faster. I mean, perhaps we won't achieve d plus k, but what I'll show you today is essentially this time, which is, it should be actually d log d, plus some polynomial in k, it will be k cubed, which is due to Alon and Chazelle, who first introduced the notion of faster Johnson-Strauss lambda. Okay? Okay, so this is what we'll be doing for most of the rest of the talk. D log d plus k. Sorry, so yeah, that bound should be d log d first of all. Yeah, I believe that AL11 achieves d log d plus k. So this is what we will achieve today. This is the Alon Chazelle paper. Yeah, I have to check actually. I forgot to check before this. All right. So, but I mean, there are also other directions where one can improve just with Strauss, which I can mention later. All right. So, so how are we going to do this, right? And I mean, what is the problem? So the problem here is that this is the picture, right? This is a matrix G. It is a dense matrix. Remember, it is every entry distributed as a Gaussian, or maybe as a random plus minus one, and you need to multiply by vector x, right? And okay, I mean, if we were to do this, basically there is so much information in the G that essentially we have to touch it all, right? Or at least this is the expectation. And really it is costly because the matrix G is dense, right? So the meta approach is to try to say like, okay, can we use a matrix G which is much sparser? So perhaps we don't need to use a very dense matrix G, but we can use a sparse matrix G, and maybe this will give us something, right? And to some degree we'll be doing that, but it doesn't work directly. So suppose we essentially let me introduce this parameter S, which essentially says how many non-zero entries we have per row. Okay, so maybe we'll say that in each row we'll have S non-zero entries, which we choose randomly, and those entries will be random Gaussian variables, right? And let's see what happens, right? I mean, we can try to redo the same kind of analysis that we did for Johnson-Strauss, and again, kind of doing one-dimensional embedding corresponds to looking what happens in one particular row, right? One particular row corresponds to one coordinate, and so let me denote this function h to say which of the entries of G have been sampled, right? So h of y will be equals to 1 with probability s divided by d, essentially to be in some form of sparsity s per row. And essentially what we get is that z1 is the first coordinate of z, right? Or of what is given, say, by one-dimensional embedding is that it will be some eta. Eta, this is just some normalization constant. We'll figure out later what it is. Times the sum of h of I, wherever the element I has been sampled. And if it was sampled, then we multiply it by some random Gaussian times the coordinate of xi. Right, this is what we get. And again, kind of, it is useful to work with squares for the numbers just because numbers work out much nicer. You can compute the expectation of z1 squared, and we want this expectation of z1 squared to be roughly equal to, say, norm of x squared. And so this is just eta squared, the normalization constant, and this is just expectation of this sum. And there is one step that I need to write. So there used to be a chalk somewhere.
You put it up here.
Oh, it's in a place to put chalk. Where?
There, just.
Oh, thank you. Well hidden, huh? Right. So the step from going from here to here is very similar to what Graham mentioned for computing the AMS sketch. Namely, so let me just compute this exactly. So expectation of z1 squared is roughly equal, expectation of that sum, so this is eta squared, times sum of h of I times gi xi squared. And again, this is eta squared. Now, so this is a sum which is squared, and there are two types of terms. One form of terms are something of this sort. Sum of I equals from 1 to d. H of I j xi all square plus the sum of I not equal to j of h of I j xi times h of j times gj xj. Basically, these are sums corresponding to the same term, the products of the same term, and these are the cross terms. And because, so this is all under expectation. Right? This is equal to eta squared times expectation of this. Right? And again, because gi and gj for different coordinates I and j are independent and centrally distributed, this is equal to 0. So this is always equal to 0. Because the expectation of gi is 0, expectation of gj. What happens is that if these two coordinates collide, which can happen with probability something like 1 over k, then we will lose this signal. And the probability that they collide is roughly 1 over k, whereas we want a failure probability to be exponential in k. Okay? So this is the main problem. So you know, if you compute, you know, what kind of sparsity do we need to, you know, to address this problem? Turns out that in the end we need sparsity which is roughly equals to D. What we need to increase a lot the number of buckets, but then, I mean, then in the end we lose again. Right? This means that each element again has to be hashed a lot, and in the end, if you compute the numbers, we will not have saved on time. But you know, at least this analogy with hashing says that, well, at least if X is kind of spread around, then perhaps we can get some kind of concentration per bucket, right? If each coordinate of X is really, really small, and it is not overly disbalanced, then then perhaps it works. Perhaps kind of, you know, hashing intuition will say that, well, we'll have each bucket to kind of concentrate around what it should be. So, you know, like I'm using a lot of kind of intuitive phrases here. I mean, we'll formalize it later. I'm just trying to give intuition before I give formulas. All right, so the new plan would be the following. So first, we would like to spread around X and then use a sparse G. Okay? And this is how we implement this plan. So this is the map. Again, this is written in matrix notation. These letters are not chosen by me. These are chosen by Alon and Chazelle, and you know, Alon at that moment was a PhD student, so I'm not sure whether this has a connection or not. But anyway, so this is the map. I mean, the output Z is equal to product of these three matrices times vector X. So again, it is a linear map, and it goes through a product of three matrices. And I will explain what are these matrices, but I also want to draw roughly how large they are, so that at least you see pictorially what it means. Okay, so originally we had something like Z is equal to this matrix, which is K by D, times this X. So this is originally, right? So now this is, we've mentioned before, FJLT stands for fast Johnson-Lithau's transform. We'll have Z, which is roughly equal to like this. This is K, this is D, this is matrix P. This is matrix H, which is of size D by D. There's another matrix D, which is also D by D. And then we have our vector X. Okay, this is how it looks. Now, what are these matrices? So, starting from right to left, D is diagonal. So, this is what like if I were to tell you much about matrices D and H, this looks even worse than before. I mean, this is like multiplying X by D matrix, which will take you D squared time, right? As opposed to D times K. So, you know, hopefully these matrices have more structure to them so that we can do this multiplication faster. And indeed, we do have structure. In particular, this matrix D just has all the non-zeros are only the diagonal. It's really just a diagonal matrix. Basically, it multiplies each coordinate of X by some number. And in particular, each coordinate of it, this is a random plus minus 1. Okay? Matrix H is what is called Hadamard matrix. And it's essentially the matrix corresponding to the Fourier transform. Okay? It is a matrix where each coordinate, it is a deterministic matrix. It is not randomized matrix, as opposed to the other two matrices. And it's a very fixed matrix. I mean, one can write it out as it is, but I mean, it's not particularly helpful. If you know what is Fourier transform, then this is essentially matrix corresponding to Fourier transform. If you don't know what is Fourier transform, then essentially the properties that we need from this matrix is that each entry is a plus minus 1 again, not random, it's a concrete structured matrix of plus minus ones. Actually, sorry, not plus minus 1, but plus minus 1 divided by root d. Again, 1 over root d is just normalization. And the properties that we need from this matrix is one, that this property, two, that it is a basis change. So if you think about this matrix as being an operator in Euclidean space, or essentially, I mean, it is some linear transform which you can think about as a function, which essentially is a rotation in Euclidean space. In two-dimensional space, it's just a rotation which preserves the norm. And finally, the most interesting part of this matrix is that the product, basically computing h times x, can be computed in d log d time. So this is the fast Fourier transform. Yes?
So you actually are saying that HD is together make a completely random, what's it called, a basis change. And given that if you don't know anything about x, then after making a completely random basis change, then it will be spread out.
To some degree, this is the intuition.
Okay.
Yes. Except that it is not a completely random rotation.
Okay, yeah.
So to describe a completely random rotation, you roughly need d squared degrees of freedom. You need a random orthogonal matrix, which roughly will take d squared random numbers, right? Or, this is the dimension of the change, right? Whereas this has only d random numbers, right, on the diagonal. So it uses much less random. If you were to have d squared random numbers to do random rotation, that would be bad, right? Because then, in some sense, we haven't achieved much, right? Like random dimensional introduction really says that, I'll take a random k-dimensional subspace, right? So I don't even need to do the entire random rotation, right? Here it is, think about, this is the right intuition, except that think about that HD is a right kind of lower randomness approximation of this intuition.
Sure. I see.
Yeah, and P is, just continuing with intuition, is this projection matrix. Essentially, what we thought originally of was G. We will not achieve optimal dimension, target dimension. We will achieve something K prime, which is what was originally called K. So we'll achieve a slightly higher dimension. And yes, intuition is completely right, but these two matrices are achieving, what we call intuitively spreading around, right? To make X as being roughly uniform. Okay, so, and basically the proof will be, the proof that this works will be to prove that these two matrices together achieve the purpose of spreading around. And that, once we spread around X, then the projection works. Right? So this is, there are two things to prove, right? That one, this works, right? This does indeed achieve the dimensional introduction, part one. Part two, to show that this can be done fast. The part that this can be done fast should be kind of obvious by now, right? So it is multiplication by three matrices. This matrix is particularly simple, right? It's just diagonal. So it's just linear in dimension of X. It just multiplies each coordinate of X by some number. This is a fast Fourier transform. This can be done in d log d. So from time perspective, this is the most non-trivial part. And this will be projection, which will be a sparse projection. So it will be particularly simple. Okay. So, first a slide on intuition of spreading around. So the idea is the following, right? The problem, the original problem, why projection didn't work, was that it was really bad for axes which are sparse. So, one addition to use Fourier transform is that Fourier transform has what is called uncertainty principle, that if you take X, which was sparse, and you compute H of X, then H of X tends to be not sparse, to be dense. Okay, this can be formalized exactly what it means, but this is not exactly how we'll be using it, so I won't quantify these terms. In particular because, it works, so doing Fourier transform on sparse x works well and makes it dense, which means that mass of x is mostly spread around. So achieves the purpose of spreading around. Now, of course, it is a basis change. This means that there are x's, original x's, such that h of x after the transformation becomes sparse, right? And in particular, this is the situation when x was dense at the beginning, right? So then, in some sense, it breaks things, right? And this is the reason why we need this matrix D and why it is random. So D introduces enough randomness that the Hadamard matrix does not break things. This is rough intuition. So now let's prove that these things work. The proof works a little bit more directly than this intuition. So let me just, call Y this transformation, H dx. What we want to prove from this Y is that it is mostly most of the mass. That Y is not concentrated on few coordinates. The mass is mostly spread around. Let me just, assume that norm of x is equal to 1. Since this is linear, basically the norm of x does not matter, right? There's no the same auto scaling. So again, what is ideal spreading around? This is what would be ideal spreading around, right? We want that the norm of y, the final norm of y, is still 1. This should not change the main purpose of all this is to not change that one. And we have d coordinates. So, what is the ideal vector that has d coordinates and has norm 1 and doesn't have one coordinate to be too large? This is the right number. It's plus minus 1 over d. Okay? On each coordinate. What will show that basically for that particular h dx, this is what we achieve. That the square, can be without squares, but it's easier to write squares than square roots. But the square of yi will be at most order log 1 over delta times 1 over d. So 1 over d is just square of this, with probability at least 1 over delta for each coordinate I. Right, so we have, so this is the ideal spreading around. What I'm saying is that what we'll have, we will have by a factor of order log 1 over d more than this ideal spreading around on each coordinate I, with good probability. Okay? And let me show the proof. It's kind of simple. Model, you'll have to believe it somewhere. But, so yi is equal to this, where hi is I for all this Hadamard matrix. And again, we don't really care about, what is the actual structure of the Hadamard matrix of this Fourier transform, except that each entry of h is either plus 1 over rho d or minus 1 over rho d. Okay? So if you look what it is, right, then yi will be equal to this, right, exactly equals to g times x, where g, is this vector. And essentially each coordinate of g is a random plus minus 1 over d. So, again, this is, think about, so g is really equal as a, this is a vector, hi, just a row of Hadamard matrix, times this diagonal matrix. This diagonal matrix on each diagonal entry has a random plus minus 1. This vector has a deterministic plus minus 1 over root d, each coordinate. So overall, the product of these two will give us a vector g, where each coordinate is a random plus minus 1 over root d. It should be simple. I hope I don't make things more complicated than they should be. So it is a random vector plus minus 1 over root d. And now we multiply this vector g by x, right? So here is, a slight trick of it. Namely that once we multiply this g times x, then yi is essentially distributed as 1 over root d again. 1 over root d is just this normalization constant times a Gaussian vector. And I mean, why is this the case? I mean, so if G were not to be random plus minus 1 or 1 over root d, but would be a Gaussian vector, then this would just immediately follow from stability. That's something that I mentioned. So now instead of Gaussians, we actually use random plus minus 1s, right? So I already mentioned in passing when replacing Gaussians of random plus minus 1s works. And it works here as well. So while this is not particularly true, the second line is true. So let me, so basically, I mean, if there is time at the end, it is a very simple kind of intuitive proof to show that switching in the three-dimensional geometry, kind of switching from random plus minus 1s to Gaussians essentially doesn't change things. In fact, it is slightly better to use random plus minus 1s. We have slightly smaller variance than Gaussians. But I mean, I don't want to go into details at this moment, but towards the end of the lecture, if there is more time, I will explain why this is the case. But at the moment, think about this kind of intuitive stuff that if you have random plus minus 1s, you can think about them as random Gaussians as well. But okay, assuming that yi is really distributed as 1 over root d times a Gaussian, then basically Gaussians are very well concentrated. So yi squared will be at most, 1 over d is a normalization constant, times order log 1 over delta of probability at least 1 over 1 minus delta. And this follows just from the probability distribution function of the Gaussian variable. Okay? So this proves this lemma, right? This proves the spreading around part. That yi, after multiplying by these two matrices, will actually be roughly spread around. So it remains only to use this projection matrix V. And the first question is, do we really need to use this projection V, right? So, I mean, we did some kind of spreading around. Perhaps we can just choose a few coordinates. So, I mean, we've taken the matrix, like we've taken the vector, right? And we rotated it somehow so that all the mass is kind of distributed around. Now, supposedly if we just take, first few coordinates, they, should take the right amount of mass, right? I mean, the proportional right amount of mass. So, perhaps this can work rather than, doing this another projection matrix V. And so maybe we can just choose a few coordinates, and each has, nice distribution. So basically, each coordinate of yi has a very nice distribution, namely norm of x times a Gaussian. And this was exactly like the case, in the original Johnson-Strauss lemma, and we just needed k of these things, right? To concentrate. So this sounds so good, except that these different coordinates are not really independent, right? This is going back to this issue that we used much less independence actually. So y1, y2 are not independent because they are all dependent on the randomness in this matrix D, right? So it's a slight issue, right? At this moment, you perhaps even ask the question like, oh, have we achieved anything? Have we completely broken the information? I mean, we have different coordinates, but they're dependent. This could be a problem. So it is not really a problem because what we have done so far was just rotations. They have not changed the norm of x. So in particular, norm of y is exactly equal to the norm of x, since h is a change of basis. It's just a rotation, right? And matrix D also multiplies each coordinate by plus minus 1. It's also just a rotation. So it does not change the norm. So at least we have not changed the norm, right? I mean, sorry, I'm just remembering what next. Okay, perhaps we need a projection matrix P, and just to restate exactly what we have so far. So if we take the maximum entry yi squared is bounded by this with probability 1 minus d times delta. So d appears here because we had to do union bound over all d coordinates. So the projection matrix that works at this moment is just to sample k prime random coordinates. So k prime is, so it's a projection matrix that maps from d coordinates to k prime coordinates. So basically, the sparsity per row is 1. We won't even touch all the entries of y. We'll just sample a few. And the idea is, the proof of this is really simple. It's just standard consideration. Okay, it's really simple once Graham proved Chernow bound, since we need to use Chernow bound. So again, because the norm has not changed, we know that the first coordinate squared plus the second coordinate squared and so forth is equal to the norm of x, which by assumption was 1. So what we'll do, we'll just sample a few of them. And the intuition is simple, right? So we have each of these entries, each of these yi squared is upper bounded by some number, right? It is roughly equal to 1 over d times some factor larger, right? So we have a sum with a lot of terms, right? And each of these terms is not too large. So this means that we can sample just a few of them to approximate the entire sum. And if you plug in the numbers, right, which is not really useful to go through now, right? The right amount, really coming from Chernow bound, of entries of terms that we need to sample is something like d times m. So it depends on the dimension, it depends on m, what is the largest value. I mean, it should be intuitive, right? And it depends on 1 over epsilon squared. This is kind of standard Chernow bound type factor, right? Times log 1 over delta times for 1 plus epsilon approximation with probability 1 minus delta. Okay, it's really, that's it, right? And if you plug in again the numbers that we get the matrix M from the spreading around step, plug in here, what we get is something like 1 over epsilon squared times log squared 1 over delta. So, in particular, k prime is slightly larger than the standard Johnson-Strauss lemma for this case. But let's live with this for the moment. So just to wrap up, again, we obtained that z squared, so z equal to the matrices times x squared is equal to 1 successful approximation of the original norm of x. It should be squared here. With probability at least something like, if you collect all the probabilities, 1 minus 2 d delta. And the dimension of z, again, is this k prime, which is somewhat larger than the dimension, the ideal dimension that we should be achieving. But here is okay, before that, so, and the total time, again, is something like d log d plus k prime. Right, so the first step takes time d to multiply. This requires the Fourier transform, times d log d. And the last step, essentially projection to k prime coordinates. Takes time k prime. So you might, it doesn't really achieve Johnson-Strauss lemma at the moment because it achieves higher dimension. But the next extra step that you can do is that once you've done this dimensionality reduction to k prime dimensions, you can do another random dimension Johnson-Strauss, as described at the beginning, with a dense matrix. Just a regular one, and you can reduce to the optimal dimension, which is 1 over epsilon squared times log 1 over delta. And it will require you a little bit more time to compute it, and you plug in this in general, in total at the end it will give you d log d plus k cubed, where this k cubed comes from doing this last step of applying regular Johnson-Strauss. Okay? And there has been a lot of work on doing this. In particular, so I think, I mean, one of the, so John Lunkers will talk about, I think, well, at least mention some, like this paper, which is some of the, it's a little bit similar. And it's particularly similar to the second step, like after the things have been spread around. So some of his work has been used in practice. So I guess this is what John will talk about, how all this relates to practice actually. What I want to mention that so there is some work on trying to reduce this k cubed, and I believe it has been reduced down to k, though don't quote me on this. Sorry?
K is actually k times k prime, right?
Yeah, and k prime roughly is k squared. So log 1 over delta is essentially k, right? Well, many parameters. Like one easy upper bound is to say that k prime is roughly k squared, is at most k squared, right? Right, so say for constant epsilon, right, this is roughly k squared, right? But it will even if this k prime were to be optimal, or close to optimal, right? I mean, we still need to do another dimension reduction to reduce to the optimal dimension, right? And that will take k squared time. Okay. So one aspect of this is that, I mean, it's much harder to remove this log g, right? Because all these approaches use a fast Fourier transform, right? So there is some of his later work actually works for the case when x itself is sparse. So you can, I mean, it's a natural question to say, can we do this faster if x itself is sparse? So for example, if x has two coordinates, two non-zero coordinates, then even original Jones-Henry-Strauss lemma would have taken just 2 times final dimension, right? You in particular did not need d log g, right? So some of the later work has been looking at the situation when x itself is sparse and whether we can do in something like sparsity of x plus maybe k.
But yeah, when x is sparse, it's very close to already being mapped down to a lower dimension.
Sorry?
When x is sparse, it's pretty close to already being mapped down to a lower dimension.
So in some sense that's true, but there are situations where d is really, really large,
Yeah.
and x is reasonably sparse.
Okay.
So, I mean, there are many situations where d, the dimension, so if you take text, for example, and you take words and you try to embed it into some vector, then oftentimes you can think about the different dimensions as corresponding to different words in the dictionary. And each coordinate will correspond how many words of that type or this particular word appears, right? So this means that your the number of non-zeros in a vector x will be maybe hundreds, or depends on how long is your text, for example. But the dimension d can be tens of thousands, right? Depends on the dictionary size of the language, right? So you don't really want necessarily to be linear in dimension d, and 100 dimension of 100 is still quite a lot, so you might want to reduce it as well. I believe John actually will talk exactly about these kind of situations tomorrow. All right, so in the last 5 minutes, I just wanted to kind of talk about, yes?
So you said reduce it to optimal k. So does that mean that this k is actually the best you can hope for?
This k, yes.
Yeah.
Yeah, very good point. I forgot to mention this. Yes, this has been proven to be optimal. You cannot reduce dimension to less than this without breaking things. However, in practice, people do try to reduce dimension to less than that, and sometimes it works. Okay, well, oftentimes it works actually, right? Yeah, I mean, okay, I didn't want to touch the subject, but in practice, people usually do not use too much random dimension introduction. Usually we'll use dimension reductions that you can set up as some kind of optimization question, right? So you can think about, like, maybe for my particular data set, for my particular endpoints, I can reduce the dimension even further just because my points are kind of nice. Maybe they are essentially, you know, I have these images, right, and stuff, right, but they are maybe kind of generally speaking, they are kind of three-dimensional objects, right, or they are close to being three-dimensional. So can we reduce to two-dimension free, actually, as opposed to this bound. And there is a lot of work, especially more in the machine learning community, where people will set up the problem this way and say, like, okay, what is the, let me set up this an optimization question. Oftentimes it's kind of NP hard problems, and you relax it, and then you get some kind of approximation. Right? Oftentimes, okay, almost always you can't prove anything about this kind of methods, even though in practice they work. And it's actually a good meta question to try to bridge these kind of 2 points, 2 perspectives, where in theory we can get bounds that work exactly right, whereas in practice oftentimes, because of niceness of your data set, you can reduce dimension to much less, except that you cannot prove anything. I'll talk a little bit more about this actually tomorrow, in a slightly different setting.
Reduce to much less by using this method.
Sorry?
Reducing to a smaller dimension but still with random projection, or we have more complicated methods?
No, there are more complicated. They will look at the data.
Like principal component analysis.
Principal component analysis is the best example, yes.
But then it's much more expensive time-wise, right?
No, not necessarily. Principal component analysis is actually relatively fast to complete. Because you have to do SVD of a matrix which is D by D, not everything. So it is, computing the matrix will take you time linear in N. But computing this singular, the top value is of a relatively small matrix actually. But we can talk about this offline. Okay, so I wanted, talking about dimension reduction, I should talk about dimension reduction in other spaces except for Euclidean space. So far we have really been talking only about Euclidean space, right? What about other ones? In particular, one of the motivating examples was this Hamming space, or maybe L1 space. So this is roughly, kind of how many people think about Johnson-Strauss lemma, is that, up to epsilons, right, you can reduce dimension to log n. And it's oblivious randomized and works with high probability, right? So can we do the same for other metrics, in particular other norms such as L1, right? So L1 is just the sum of difference of absolute values of differences between different coordinates. It's a norm of choice in certain other applications. And the answer is that essentially no. So there has been quite a lot of work on this and negative results. In particular, there is there's a paper, I believe Johnson Nower, who proved that essentially if you, a statement of the sort of, if you have a dimension reduction that is as powerful as Johnson and Strauss, then your metric or norm is really very close to Euclidean. So it's a very strong form of lower bound. And for a one, which is, a norm, it connects to things like lasso regression and kind of stuff, right? Which would be very useful to have such kind of dimension reduction for it. There has been more work kind of trying to pin down exactly what is known. And for example, for dimension D, for approximation D, the current bounds are somewhere between here. And this is even if the dimension reduction takes into consideration the actual endpoints that you have, not even oblivious. So this is, the upper bound is something like n divided by d. Right? So for one perceptual approximation, this is nothing. This is order n dimension. This is very different from order log n. And just I'll quickly tell you that kind of to connect back to Graham's lecture. So for L1, we can do slightly different things that looks a lot like dimension reduction, but is not really a dimension reduction. So here is one thing that is not really like Johnson-Strauss lemma. It doesn't achieve high probability statement, but it achieves something, and it is useful in many applications. So it is the analog of Euclidean projections in L1. So how from algorithmic point of perspective, kind of okay, can we do a similar kind of things for L1? In particular, what do we need? What did we use? Kind of the main property in Euclidean space that we use is these Gaussian projections, where we said we take these Gaussian vectors and we take our one-dimensional projection was really a product between a Gaussian vector and our input vector x1, x coordinates x1, x2 up to xz. And we said that it has stability property where this sum is distributed as g times norm of x, L2 norm of x, right? So there is a natural question, now you can, pull out your matbooks and say, are there distributions similar to G, where, I would replace, this would not be G, but some other distribution such that this sum is distributed as something times 1 norm of x. Okay, it's a valid question. And yes, there is such a distribution. It's called Cauchy distribution. And it is one stable. This is two stable because this is two norm. This is one stable. Essentially, if C1, C2 up to CD is distributed as a Cauchy distribution, now I'll tell you in a second what it is exactly, then this sum is distributed as another Cauchy distribution times 1 norm of x. Right? So this looks awfully like this, right? And should be useful. And this is what is the Cauchy distribution. So this is the PDF of the distribution. It is essentially up to normalization 1 over x squared plus 1. And you can parameterize it with some parameters, right? But take a look, for example, at this. What is the right one? This violet thing. This is a picture from Wikipedia, so had a little bit more graphs than I needed. But this violet one is exactly the Cauchy distribution as described here. And now the question is, why don't we just take this Cauchy distribution, plug it in where we did Gaussians before, and not get the Dimension reduction for L2? And so what's wrong? The problem is that Cauchy distribution, in contrast to the Gaussian distribution, is heavy-tailed. So it's something like 1 over x squared plus 1, as opposed to Gaussian that are distributed decay exponentially. And because of this, the Cauchy distributions don't even have an expectation. You don't even have expectation of the absolute value of the Cauchy distribution. And basically you can't get the type of concentration that you were getting for Gaussian. But this is still useful in many applications, and the idea of using one-stable distributions for approximating L1 norms has been introduced by Inding in 2000. And indeed, you can take something like a map as before, exactly like multiplying by Cauchy vectors, and you'll get exactly the same kind of statement that each coordinate is distributed as 1 norm of x times a Cauchy. Again, 1 norm of x will not concentrate as before, so we don't have the same thing as the previous sum of squares of Gaussians would concentrate. But you can estimate the norm of x, basically, 1 norm of x from this of x by taking the median of absolute values of coordinates. And this is something that Graham mentioned that is very useful in streaming. So so it is not a dimension reduction in the sense of we don't map back into L1. We map into some space. Basically, it is a sketch. It is not exactly a dimension reduction. But, you can think about this as a form of dimension reduction. Just that the estimate that you make at the end is not computing 1 norm of f of x, but taking the median of absolute values. And basically, Graham mentioned why median works, so I won't repeat. And again, this gives a sketch. So for example, this kind of sketch is already useful for nearest neighbor search computation. As I mentioned, going from kind of trivial scan to slightly less trivial scan where you first do dimension reduction and then do the scan. Since once we do the scan, we don't really care which how do we exactly compute the distance between our query and the data set. All right, I'll end here.